Welcome to module 3 of database management systems course. We started discussions introducing the database management systems in module 2. This is the second and concluding part of that discussion. So, this is what these are the aspects that we had discussed earlier, starting from level of abstraction to the outline of database design. In the current module, we would like to understand the models of database management systems a little bit more, and we will try to familiarize with the concept of major components of database engine. We will elaborate on those and we will familiarize with the basic architecture of a database management system, some of the internal components, and will present a brief historical perspective of the DBMSs. So, this is the outline that we will follow. So, we have already discussed about the database design. I would like to raise a few further issues about that. So, we have seen that there is a logical design which is driven by the business decisions and refined by the computer science decisions. There is a physical design as well, and based on that we had I had presented this particular table asking whether this database is whether this is a good design or not. So, let us have a little look into this. For example, we have introduced the department name and the building in which the department is housed. So, if we look at, there are multiple instructors, say let us say Professor Einstein, who teaches in the physics department that is housed in the Watson building. And if we look through, there is Professor Gold, who also teaches in the physics department, and naturally that is housed in the Watson building. Now, the question is, so physics department, if it is housed in the Watson building, then all the instructors in this table, all the instructors who are part of the physics department would have their department housed in the Watson building. So, there is a certain issue of between these two, there is certain issue of redundancy. That is, the same information is given more than once, which is not a very desirable thing. The consequence of this could be, suppose tomorrow the university decides to move this physics department from Watson to the Taylor building. This will mean that once this is moved, then this Watson will have to be changed to Taylor. Also, this Watson will also have to be changed to Taylor. All instances of Watson that corresponded to the physics department in this table will have to be changed to Taylor, and that is not a good scenario. So, it is not only that we have redundancy, we have potential for anomaly. That is, we might, the application program, the application programmer might forget to update the building, say for this entry, then we will be in an inconsistent database. So, to put it in simple terms, that this is not a good design, and there are several issues to consider in terms of whether some design is good or some design needs refinement. So, need to come up with a methodology to ensure that each of the relations in the database is good. So, we primarily follow two approaches in doing this. One is using the entity relationship model, which models the enterprise as a collection of entities or concepts, or if you are familiar with object orientation, classes, and the relationships that hold between these entities. So, in an university database, the entities are students, courses, teachers, and the relationships are a teacher teaches a set of courses, a student attends a set of courses, and so on. The teachers supervise a set of students for projects and so on. and then represent them diagrammatically in terms of a ER diagram, entity relationship diagram. And once that has been done, then we try to follow a certain normalization theory. This normalization theory tries to capture that what are the properties that must hold in this database design, that must be satisfied on this database design. In terms of what is known as database dependencies, there are varied forms of dependencies, functional dependencies, multi-valued dependencies, joint dependencies, and so on, and try to formalize and evaluate whether a design is good or it's bad, test them for quality, and then normalize to make them better, make them the best possible that can happen. So, that is this is something that is starting from the entity relationship model, which captures the real world, to the actual database schema. There is a process of representation and then capturing of ground truths that hold in the database, should hold in the database system, and then normalize the database is a basic requirement of the design approach. We have talked about object relational data models, few more points about that. That in a relational model, everything is flat, every value is atomic, in the sense that everything, if you look back and think in terms of C, then every field is a value which can be a simple, built-in type, like integer, like fixed length string, variable length string, a floating point number, like that. But I cannot have a composite, object kind of fields. But in a relational data model, we extend, in the object relational data model, we extend the relational model by including the object orientation and the constituent constructs to deal with added data types, higher data types, where attributes are allowed to have complex types, non-atomic values that may allow things like nested relation, that is, a value could itself be a relation, could itself be a table, and but we try to preserve the relational foundation, and we will see what those foundations mean, and provide upward compatibility to existing relational databases. So, this is what the basic concept of object relational data models are, and as I said that we will just glimpse through it, but this is not the primary objective that we will try to cover. In contrast, the XML, extensible markup language, was defined by W3C, and it was originally intended for marking up document languages. Not as it was not designed as a database language. It was designed for marking up. So, it is kind of saying that this particular element should be put in capital, this should be in blue color, this means a verb, this means a paragraph, there should be a page break here, those kind of markups. But subsequently, it turned out that the way XML deals with different components in terms of tags and the ability to create nested tags makes a great language for exchange of data, as I explained in the last module also. So, it is become the basis for all kinds of new generation data interchange format. So, as I explained that any database should be able to convert the data instances of the tables in terms of corresponding XML format, and then you take it to some other database where you, with which you are intending to interchange the data, and that target database should be able to import from that XML structure, and it has become widely available that you have different tools for parsing, browsing, and querying XML content, document, data, and so on. So, if you are familiar with C programming, I hope so you are, you can look up certain XML parsing and try out. They are great tools to learn. Moving on, let us briefly look at what is the core of a database management system, the database engine. The database engine primarily contains three major components: the storage manager, the query processing engine, sub engine, and the transaction manager. The storage manager is a module or a collection of modules in a database management system that provide the interface between the low level data and the application program. So, we have looked at the storage manager is the one which is a bridge between the physical level of abstraction and the logical level of abstraction, then finally to the view level of abstraction. So, the storage manager has to deal with interactions with the operating system on which the DBMS is kept. The file manager of the operating system, it is responsible for efficient storage, retrieval, update of the data. It is responsible to make sure that if there are certain problems in the file system, then the data is not corrupted and so on. So, the issues certainly that involve are the access to the storage, the organization of the files, and very importantly indexing and hashing, and we will talk about the concept of indexing later in the course. It primarily says that if I want to for example, you can simply understand that if you have a large chunk of data that you want to organize for efficient search, then you can use binary search tree in simple algorithm terms. The binary search tree needs to be organized in terms of one data component. We say that, well, there is one value based on which you can say that comparison is done, so that at every node, if that value is smaller, you go to the left subtree, if that value is larger, you go to the right subtree, and so on. So, if we want to organize the records of a database system in terms of such a binary search tree, then the question certainly is which field do I use for the search tree comparison. Now, whatever field I use for search tree comparison, on that field the searching would be very efficient, but if I want to search on a value for a different field, the searching would not remain that efficient. So, indexing is a mechanism by which you can actually create auxiliary search trees on multiple fields, so that the search on multiple fields can be made efficient, and we will talk about this later when that particular module comes up, but the storage manager has to deal with such issues. Moving on, the query processing is if we have already talked about the language, the DDL, the DML, the query language. So, it is some kind of like the C program, it is some kind of a text based programming code. So, naturally that code needs to be parsed and translated as we typically do in a C compiler. So, there needs to be a query compiler. So, it parses and analyzes the code, but translate it unlike the C program, which translates the C program into an intermediate code and then into the binary instructions of the machine, the assembly binary instructions of the machine. The query translator translates the query into relational algebra expressions. I said that there are two kinds of languages, the commercial query language and the pure language. So, it translates it in terms of a program in the pure language, which could be a relational algebra language, and then it tries to optimize. So, that's a critical term to be noted, that there is an optimizer. So, this optimizer is a critical component which tries to make sure that the query, when it is run on your data, will run with the most least amount of time in an effective manner. So, and then an execution plan needs to be decided. You will be able to understand this when we go to the actual relational algebra. Execution plan basically says that if there are multiple operations in that query to be performed, then how those operations, in which order they should be performed, and where should temporary tables be used, where they should be skipped, and so on. And then once that has been done, then it passes on to an evaluation engine which actually runs that query on the data that you have, the instances of the data that you have, and that brings out the resultant query output, which is another table of results that we get. So, this query processing is a core part of a database engine, which actually allows us to write text based queries and retrieve data efficiently, update data efficiently, insert data efficiently, and so on. So, So, when we do this, that we need to look at alternative ways of evaluating a query. There could be different ways to write the same thing. These are called equivalent expressions, and what are the good algorithms for doing each and every operation. There is a cost between good and bad way of evaluating. So, this has to be understood, that the same thing you can compute in a, you have seen these similar concepts in normal programming languages also. I mean, we have seen for example, for sorting, there are several ways to sort, and some are better, some are not as efficient. So, the similar things in terms of a query needs to be evaluated, and the cost between good and bad ways need to be figured out. So, then we need to estimate the cost of every operation. It depends on the information of what has happened in the past, the statistical information, and need to estimate those statistics for intermediate results. These are the couple of things that the query processing sub engine in a database will do. So, beyond the storage manager and the query processor, we have a transaction management system, which is very, very critical and core of the database system. It is primarily has to deal with two fundamental issues of a database. One, what if a system fails? See, database systems are unlike the programs that you have written so far. A program starts, executes and ends. The program always deals with transient data. The data did not exist before your program started. It ceases to exist after your program ends. So, a program, however complicated, however important, has a limited lifetime. A database, in contrast, has a much longer lifetime. It deals with persistent data. That is very important to understand. That is, each application, whether I am doing a bank fund transfer, whether I am making a credit card payment, whether I am checking the balance, or I am booking a railway ticket, whether I am purchasing a book from Amazon, each one of the applications are like the normal program. It has a fixed lifetime. I start it, I do certain operations, I am done with it. But the data that is behind it, the data of my accounts, my account balance, my transactions, my different bank charges, all that need to stay on and on and on, and beyond every particular operation that I have done on the database. So, which means that if this database system fails at some stage for some reason, then we have an enormous impact of that, and that is not something that we can absorb, that is something that we can accept. So, a database system has to come with the concept of recovery. It must be possible, if the system fails, it must be possible to recover it to a certain earlier point where it is consistent. So, transaction management system is responsible to guarantee this kind of recoverability of databases. Then the other question that we have discussed about earlier also is multiple users are accessing the same database, the same set of data at the same time. So, how to make sure that more than one user can concurrently use an update without the data getting inconsistent. That is, as I had mentioned, there is only one seat available, one berth available on a particular train on a particular date, and two users at the same time has initiated a booking. It should not happen that both of them get the booking. So, one should get, one should not get, and that needs to be, the complexity is high for this kind of decisions, because the databases as applications are significantly distributed. Indian Railways have no idea of who is going to do what booking of which berth from where at which point of time. So, transaction management system is, as the name suggests, defines something called a transaction, which always keeps the database consistent and operable. So, it is a collection of, a transaction is a collection of operations that performs a single logical function in a database application. This is very, very critical. It is a collection of operations and performs a single logical function. So, it does not do anything and everything, it just does a single particular logical operation, and that is what forms the transaction. So, a transaction management system is a component that ensures that with all these transactions happening, hundreds and thousands of transactions happening every second in a database system, in a typical database system, the data should still remain consistent, in a consistent state. In spite of failures, in spite of concurrencies, it must make sure that at no point of time it should happen that an amount has been debited from an account and has not been credited to account, or an amount has been credited to an account and has not been debited to the corresponding account, or the same seat, same berth is booked by two persons at the same time, and so on and so forth. So, this also includes concurrency control manager, which controls the interaction among different concurrent transactions, which ensures the consistency in the database and provides the total safety. So, in total we have seen the different components of the database engine, comprising the storage manager, comprising the query processor and the transaction manager. Now, we move on to we will just have a quick look in terms of who are the typical users of a database system. So, if we see the grossly the users of a database system can be grouped into, I mean you can group it in multiple different ways, but this is a typical way to group that. You have the naive users, those like those the secretarial staff who sits at the teller of the bank. Now, that person just needs does not know database management system, but that person just needs to know the particular application. He knows a few set of screens, graphical screens, what needs to be filled up where, which button needs to be clicked and so on, and can use this database through an application interface. So, this is a lowest level of user. Then you have the set of application programmers, about whom I talked about in my course overview presentation, that application programming is a big chunk of IT services that databases need, who actually write the application programs. While the naive user is merely using it, application programmers are responsible for writing, coding these application programs. So, they need to understand the database designs, they need to understand how to write the query language, how to fit with the application data, input, output, all these systems. The next level are the analysts, who are called the sophisticated users. So, they design different kinds of query tools, they are responsible for the design of the database, that is a schema, the different constraints, the authorizations and so on, and manages that over a period of time. When the application requirements change, they might need to redesign the schema, migrate the data from an old schema to a new schema. So, analysts are higher level of programmers, they have far more solid understanding of the database management system to be able to design different kind of query tools that the application programmer will use. And at the end there are database administrators. So, database administrators are people with specialized rights who can do a lot of privileged operation on the database. For example, taking backups of databases, for example, creating different users. For example, if there has been a failure, then how to do the failure recovery scripts, recovering the database and so on. So, they do all kinds of administration tasks, but not the usual day to day data maintenance and query processing and so on. So, if you would like to know your positions, then I would say that through this course you are going to position yourself amongst the application programmers and the analysts, and as I mentioned at the first half of the course, is focused on application programming aspect, and the second half would be more focused on the analysis and some of the administrative. We will do little bit of administration, but not really serious administration tasks. Now, we will take a quick look into the database internals and architecture. So, I will take you to this diagram. I am sorry, this diagram is little small in terms of the script size. So, please refer to the actual presentation. So, if you look at the top, here is the users. So, just trying to show what different users use. This is the query processor that we have known. So, the query processor gets a query, and so that naturally the query comes from the application program. So, the compiler, linker, these are the basic processing, then the compiler organization, the evaluation engine, which actually takes care of the processing of the whole query, and then it goes to the storage manager, which is now taking this, whatever the evaluation engine needs to do has to go through different modules in the storage manager, which we will talk about these modules when we do have a discussion module on the storage management later in this course, and we will then talk about what is a file manager and what is authorization and so on. But these are the subcomponents, that the storage management needs to do, and then the storage manager is the only one who deals with the actual data, the actual disk storage, the different files and so on. So, as you can see that the whole system is kind of layered in terms of, so this is your basic physical layer that you have, and this is your final view layer that you have, and in between this is a logical layer that you deal with. So, you can see that the abstractions as we had talked about are also mapped in terms of the way the actual database system architecture is managed, and finally, the data stays in the disk storage, which ensures that whatever data I have is actually persistent in nature, it does not go away. Any data that stays within here or within the application interface is transient. So, that data, these data are transient, they will disappear as soon as the application is over, but these data are persistent, they exist beyond this, and the architecture supports that whole gamut from of all applications or transiency of the applications based on the persistency of the data at the storage. So, that is the basic architectural view of a typical database system. So, the actual architecture will be far more complex, but we just want to take a schematic view so that we can understand it better. So, the actual architecture may again vary based on the computer system that you are using. It could be centralized. We will talk about some of these at later modules. Centralized in the sense that there could be one database server, or a group of database servers at some physical location connected together, to which all applications, all user will connect to. It could be in terms of a client server model, which is a very typical client server model that the programming systems have. So, that typically for example, any of the internet based database applications we are looking at are necessarily client server in nature. What you are doing in the browser is a client, and there is a server back far back there, there are multiple tiers in between them. Databases could be single processes, or for performance they could be in terms of multiprocessor. Parallel databases, the data sets themselves could be so large that it may not be possible to search on them through a single processor in a reasonable time. They could be distributed, the data itself could be distributed, tables could get so large that I may not be able to keep them at a single point. So, these are different aspects of complex real life database system that exist, and we will deal with some of those aspects over the course of time. But you have to keep in mind that a final architecture of a database and its associated application will have some of these factors that you will need to know and maybe decide on. In terms of history, well, I mean, I will not go through each and every point here. This is more for completeness and to give you a sense of how things have been going. So, database systems started in the 50s and early 60s, then major developments of these relational models and all that started happening in the 70s and in 80s. Really it proliferated large in terms of prototypes and commercial systems, parallel distributed systems, object based systems started happening in 80s. 90s it really exploded in terms of large decision support, data mining applications, applications, widespread use of internet based data applications and systems, emergence of Google and all that. From 20s early 2000, it has been XML and automated database administration, and now what we are facing in are the big data, which are certainly aspects of other courses, but at the back at the last layer there often is a strong relational system that exists. So, to summarize, in this module we have introduced the models of database management system, the major components of a database engine, and discussed about the internals and architecture. And this will conclude our discussion on the internals of database management systems. And next we will move on to exposing more on the relational module.